Good morning, everybody, and welcome back. My name is Dulce Alere, and I'm here with NoCo HBA. Today, we are on webinar 5 of Construction Workforce Training, Infiltration versus Ventilation versus Manual J. Remember, if you'd like to check out other webinars we've offered so far in the series, please visit our website, NoCoHBA.com. Thank you to our wonderful sponsors, BUILDTank, City of Fort Collins, and Xcel Energy. Let's get started. I'd like to introduce Brad Smith from the City of Fort Collins. Brad, take it away.
Thanks, Dulce. So sorry about not being able to be visible on the screen today. I was having some technical issues at home, and I'm on a different computer that does not have a camera. Regardless, I'm here. Thanks for attending, and we do have one more series in this session next Friday, so hopefully you all get a chance to register and attend that session. I'd like to kick it off by introducing Robby, which I've done in the past. And I'm sure a lot of you have heard this already, but Robby is a great resource in Northern Colorado and really all over. He's been in this industry for a good number of years and really was one of, I think, kind of the founding fathers of a portion of this industry. So Robby has a lot of great expertise, and I'm happy to have him here presenting on this series and be a part of this series with NoCo HBA. I will also be posting in the chat a quick link to an outreach session that the City of Fort Collins is doing to kind of help shape energy efficiency and renewable energy in the City of Fort Collins. So if any of you would like to participate in that, I will post the link and you can visit the website, and up on the right-hand corner of that website, you can share ideas or attend a workshop. Again, the workshop that we're presenting in August is more renewable energy, and it centers around building efficiency as well. So with that, I will kick it off to Robby and enjoy.
Great. Thank you so much, Dulce and Brad. And thank you again to the City of Fort Collins, Xcel Energy, and the Northern Colorado HBA for hosting this event. Really appreciate it. I'm going to turn off my video now so that we can all concentrate on the slides and I guess my voice here. And we're just going to dive straight in here. Our plan today is to talk more about infiltration, ventilation, and Manual J, why we need to have the conversation, a bit of a talk about the building envelope and how air works, and then we'll go through some things that we need to look at in Manual J to understand if we have a good heat load calculation or not. So the main reason we're really having this conversation is that our HVAC system will not work, basically, if our thermal envelope isn't working. So we really need to begin the concentration on the building thermal envelope to ensure that the other systems that rely on that building thermal envelope will actually function and work and perform the way that we want them to. We know that the energy loss and the energy gain is dictated by that thermal envelope. The continuity of the insulation and the air barrier systems around that thermal envelope resists the flow of energy from inside the house to outside the house in heating season, and from outside the house to inside the house in cooling season here. So the big issue is not necessarily that the thermal envelope is there, but as it's been installed, will it actually work and function? So we have groups like NAMA, which is the North American Insulation Manufacturers Association, putting out checklists, and other groups like Energy Star putting out checklists, and even the IECC in essence has a checklist baked into its code, which we'll look at here in a few moments, all to ensure that the thermal envelope is installed well, but not just that it's installed well, but that it will ultimately perform the way that we want it to perform to help govern the amount of energy that is leaving or gaining into that structure that we're trying to build here. So this is a basic outline of the construction process, kind of simplified down. And the main reason we want to look at this is to realize that when we talk about designing an HVAC system, that process generally happens at the very beginning of the construction process. So somewhere in this design and pre-construction meeting, we're beginning to talk about designing and implementing an HVAC system with that greater design of the house there. The problem is that we're making assumptions at that point. We're making assumptions about how that building envelope is going to be constructed. We're making assumptions on how airtight that house will be. And if those assumptions aren't carried out properly, then our HVAC system will not work, because we're not going to go back and change those assumptions, or we haven't really gone back and changed those assumptions. And in some cases, after the design work is done and the HVAC, let's say the duct system is installed in that house, it's really impossible to go back and change those things. You know, how can we resize the duct system because our assumptions were wrong? The building thermal envelope wasn't created properly there. So in this HVAC design process, there are basically three main components of this design process. The first step is to calculate the heating and cooling loads. And again, that happens at the beginning of the construction process or design process for the house as it's being built in totality there. Then we select the equipment with the capacity to meet the loads. That's the manual S process. And then ultimately we're laying out the ducts and deciding which ducts to put where and how to run the returns and supplies in that house. And that's the manual D process. So this process begins with calculating the heating and cooling loads, and calculating those heating and cooling loads of the house is dependent again on describing the thermal envelope and all the different components of the thermal envelope that are separating conditioned space from unconditioned space, that are governing how the heat loss and heat gain are leaving and entering that house. Our ultimate goal in this process is to have a house that has consistent temperatures from room to room and floor to floor. The reality that we're still seeing out there, unfortunately, is that we're getting oversized or undersized systems in our houses instead of right-sized systems. So we're having to pump in additional energy into our houses to heat and cool them because our thermal envelopes aren't executed well, or our thermal envelopes are executed well and people are still oversizing the equipment or undersizing the equipment there. So we need to figure out how to have this balance, this synergy between the building thermal envelope and our HVAC systems and HVAC design, so that we're getting right-sized equipment instead of oversized equipment or undersized equipment. And this process begins by understanding infiltration, ventilation, and our thermal envelopes well. So we're going to begin by looking at this difference between infiltration and ventilation here. To begin with, when we're talking about air leakage is really described by this notion of infiltration. Infiltration is the unintentional or accidental movement of air into a building. So the infiltration is talking about air movement, but it's talking about air movement that's coming into the building. Air leakage is also described by exfiltration. And exfiltration is this unintended or accidental movement of air out of the building. So air leakage, combining infiltration and exfiltration, are basically how we describe air leakage in our houses. And air leakage in our houses is really governed by this unintentional, unpredictable, and accidental movement of air in and out of our houses there. So that's what we need to remember. Infiltration is a load and exfiltration is a load, and it's accounted for in our HVAC design through the infiltration input that we do in that design process. And in essence, we're measuring infiltration by the use of a blower door test, and we can use an accurate infiltration measurement in the HVAC design if we so choose. Otherwise, we're going to use an estimation there. So ultimately, we're striving for control and predictability of this air leakage by building our houses tighter and tighter. And that's one of the big things that's not being implemented or accounted for in our HVAC designs is this move in the construction industry to build a tighter and tighter home that has greater and more control and predictability of the airflow in and out of that home. So that's air leakage. Again, it's this unintentional or accidental or random movement of air in or out of our houses. Now, ventilation is a little bit different, because ventilation it happens after we've gained control and predictability of the air. So we've gained control and predictability of the air by sealing up holes in the building envelope that infiltration and exfiltration can go in and out of. So the air leakage portion has been taken care of. Now we have control and predictability of the airflow in our houses, and now we can mechanically ventilate our homes. So we're mechanically ventilating our homes, which means that we're taking air in or out of our homes at a specific rate, which means that a specific quantity of air measured in cubic feet per minute are leaving or entering that house at a specific schedule, which means that we're putting it on a time. It could be as long as running that mechanical ventilation systems 24/7, but we sometimes run it maybe 15 minutes every hour, or which equates to about 8 hours every day. And so this ventilation also has a load that is accounted for separately in our HVAC designs through that calculation and flow rate measurement there. And one of the things that came up to me recently that really brought this to a head was a code official who didn't want to count mechanical ventilation and infiltration separately as two different distinct loads in our houses. And we'll talk about that in a little bit when we start talking about exhaust ventilation, because it's a little bit difficult to separate the two when you're looking at an HVAC load and manual J. So some but not all ventilation systems are able to provide additional features in our system. Some allow you to bring in air or exhaust air from specific sources in your houses. And some HVAC or some mechanical ventilation systems allow you to filter and distribute that air as well. But two of the main whole house ventilation systems that we utilize in our houses, exhaust and supply side ventilation systems, really bring air in and out through holes in our building envelope. But again, it's at a specific rate and a specific schedule. So although ERVs or balanced ventilation systems are probably the best ventilation systems in our homes, we do have these other types of ventilation systems that are kind of introductory ventilation systems for builders, because often they're more cost effective there. The two primary functions of the ventilation system in our houses is to provide fresh air for the occupants and to provide that background moisture control in our houses. So ventilation is really fundamentally different from infiltration or air leakage in our homes. They're both accounted for, they both have loads, but they're accounted for separately in our manual J calculations. Our ultimate goal here is to have comfort, efficiency, and performance. And so we need to look at all the loads that are providing there, and to ensure that our building thermal envelope is sound and productive for us, just like the coats that these people are wearing. If these coats are going to work, they're going to work because they have the continuity around the whole building thermal envelope there. And so the codes are beginning to understand this and beginning to spend even more concentration on the building thermal envelope here. The IECC has a specific section saying that the building thermal envelope shall be represented on the construction documents. How you represent it on the construction documents is really left up to the designer, the architect there. But the building thermal envelope is a defined term, and we see that it's ultimately an assembly of things, not just one component of that building thermal envelope. So in most cases, we're seeing that the building thermal envelope is a combination of kind of interior functions, which usually is a continuity of our drywall around the building and the exterior sheathing together, enclosing the thermal part, is creating that greater building thermal envelope that we're trying to depict on our building envelopes. The code continues by defining air barrier systems and defining the need for the continuity of those air barrier systems. And again, those air barrier systems are assemblies of things, not just one component in our assembly there. So the code continues and says again, once again, that we in essence need to do this red line test. And the red line test was something that was created by Joe Stiebrick and some others out there that says that can you take a sectional drawing of your plan set and without lifting your pen off the piece of paper, draw a continuous line around that thermal envelope where it's supposed to be. Now, sometimes it's very difficult to do in reality out in the field, and that's where inspection comes in. Any inspector, third party or code official wise, should be able to help you create your sound building thermal envelope if you come to a section where your continuity is in question there. But this building assembly and air barrier assembly and system, again, in its simplest form, is the continuity of the drywall system adjacent to the thermal barrier all the way around on the interior of our houses. So the code is really pointing out areas where that continuity might not happen, like behind a tub or in a HVAC chase, where you might have to add a supplemental air barrier to enclose that insulation when it's in a wall cavity or a floor cavity or potentially in a roof cavity there. And then the continuity of that exterior sheathing as well, all the way around the house. So all holes and penetrations in that exterior sheathing need to be sealed up as well. Now, the house wrap can be a supplemental air barrier system, but in most cases, our house wrap is really a drainage plane. It's a moisture barrier for bulk water on the outside of our homes. So that control layer for moisture is often achieved using a drainage plane out there. Now, ultimately, the function of these air barrier system is to specifically enclose air permeable insulation, because we want to have that stagnant pocket of air inside that air permeable insulation. So you're going to hear this notion of more and more six-sided enclosures in those assemblies there. And then to gain control and predictability of the airflow in our houses, the thermal control in our houses, and moisture control in our houses, because again, so much moisture moves with air here, and we'll talk about that again. The code continues to say we need to install our insulation well, and it says that we need to follow manufactured instructions, and it goes a little bit further that says that we need to follow the criteria that's listed in table R402.4.1.1, which is the insulation and air barrier table I'll show you here in a moment. But manufactured instructions describe how insulation works and how it needs to be installed so that it actually works. And it turns out that insulation works the same way in a building as it does the clothes that we wear to protect us from the cold outside. So in essence, this person is putting on a fleece jacket, and the object of that fleece jacket is to insulate the body. And that fleece jacket is trying to trap a pocket of air. It's actually the pocket of air that resists the flow of energy from this person's body to the ambient air outside. And the fleece jacket is beginning to define the thermal boundary between the person's body and the ambient air around her here. The object, however, is to have a stagnant pocket of air. So the pocket of air resists the flow of energy, but if that pocket of air doesn't stay within the fabric or the insulation there, we're not going to have that resistance to the flow of energy. So therefore, we often on cold days, we add a layer, we add a air impermeable layer or a piece of nylon fabric that stops the flow of air that will help us trap that pocket there. So in essence, we have an assembly now that is working. We have an interior air barrier, which is our skin. We have our thermal barrier, which in this case is the fleece jacket, and we have an exterior air barrier, which is the nylon shell on the outside of the jacket. And we have a system that works and works well to trap a pocket of air and give us resistance to the flow of energy from our bodies to the outside, keeping us warm on a cold winter day. So the same thing is actually happening in our homes here. We have insulation in our cavities there. It resists conduction by trapping pockets of air, but it doesn't resist airflow if it's an air permeable piece of insulation. Therefore, when we're talking about wall cavities and floor cavities, we have to have six-sided enclosures, six-sided air barrier systems around those cavity insulation so that we resist the ability of those air pockets to leave and take energy with them there. So we're fighting against this myth that all insulation products stop the movement of air. Only air impermeable insulations stop the movement of air. And often only if they're blown or installed at the proper thickness. So some examples of air impermeable insulation, or insulation where you really have to concentrate on putting supplemental air barrier systems in your home, are fiberglass bats and dense blown cellulose and fiberglasses products there. And then air impermeable products would be foam boards and closed cell foams if it's blown to the correct thickness, and open cell foam products if it's blown to the correct thickness there. So we need to understand, again, the materials that we're installing and how to install them so that we can gain that sound building thermal envelope out there. Now the code continues to help us understand how to install these materials with this table. This table is in essence a checklist that helps us install our insulation better and ensure that we have the proper air barrier systems around those pieces of materials in each of the components there. So the table breaks down the component that it's looking for, from general components to specific components like at ceilings and walls and crawl spaces. It tells us what we need to do from an air barrier perspective and what we need to do from an insulation installation perspective there. If we follow this table in a single family home, we should not have any problem meeting the air leakage requirements of 3 air changes per hour there. We might have to do additional things to get lower than 3 air changes per hour, but on average in Colorado, our air leakage rate for a single family home is about 2.5 air changes per hour. And that's largely because people are understanding and implementing this table or the Energy Star checklist, thermal enclosure checklist, which is basically this table. Those types of things are helping us get to a more airtight house. We do have some issues still with attached housing, largely because of the area separation wall there, and we just don't have time to go into that today. So air is a problem, and air is a load in our houses that we need to control. When I think of air, I think of a freight train. So I like to equate air to this freight train because this freight train is carrying a load from point A to point B, in this case coal, which is energy. And it's ultimately depositing its load and leaving it somewhere. So it's taking it from point A to point B and then leaving it at point B. Air, on the other hand, is also carrying a load. It carries energy, it carries heat, it carries moisture, and it carries pollutants. The problem is that it can also deposit its load, but it deposits its load randomly. It might carry its load into a wall assembly and deposit its load there, or it might carry its load all the way from inside the house to outside the house. Where it deposits its load is the problem. We don't know always where it's going to deposit its load. But we do know if we build a house tighter that it's less likely to deposit its load inside of a building assembly and therefore create condensation and building durability issues inside of our wall assemblies or floor assemblies or ceiling assemblies. So you often hear this question being asked, can a house be too tight? And I hope we all understand and agree that the answer to the question is no, and that we're ultimately asking the wrong question. We want to gain control and predictability of airflow, and in order to do that, we need to build a tight house, and we need to build that house as tight as we possibly can. And then we need to ask that correct question, are our houses underventilated? And unfortunately, it's still true that most of our houses are underventilated there, and we need to continue to strive to build tight and ventilate right there. Now, the code is helping us to a large extent now, because the code is requiring us to achieve a specific rate of air leakage and air tightness in our houses, and it's also requiring us to ventilate our houses correctly there. And as we get better and better at that, we'll build tighter houses, and we'll choose better balanced ventilation systems for those houses that we build out there. So our ultimate goal here, again, is to gain control of the airflow in our houses, and then through ventilation, gain predictability. We want as much predictability as we have and we know when we go to McDonald's. I know very predictably that when I order a Big Mac at McDonald's in Denver or Fort Collins or in New York City or in Paris, France, I know exactly what I'm going to get. I know exactly how I'm going to feel afterwards, because there's so much control and predictability about that particular product. That's what we want with the airflow in our houses. And airflow in our houses, just to review again quickly, is driven by two things. We have to have a hole, and we have to have a pressure difference across that hole in order for air to flow. So we have a lot of holes in our homes, and we're getting better and better at sealing up those holes in our homes. But the pressure across those holes are the things that we have difficulty maintaining and having better control over. But to understand that pressure across the building thermal envelope, let's think about this balloon again and recap this balloon demonstration again. So if we think of the rubber membrane around this balloon as the thermal envelope in our house, we see that it's separating the external pressure from the internal pressure here. However, if I untie the string that's closing off this balloon, I've connected those two pressures. I have a hole, and I have a different pressure on either side of that hole, because the outside pressure is going to be greater than the inside pressure in this case. And that outside pressure is going to collapse the balloon. It's going to push against the balloon, push air out of that hole. And now I have a hole and a pressure imbalance across that hole, and we're going to collapse that balloon. We measure the airflow in cubic feet per minute. A cubic feet per minute is about the size of, or a cubic foot of air is about the size of a basketball. And air is defined by the volume of air that's inside that house, inside that building thermal envelope of that house. Air that goes into that house means that air has to go out of that house, or air that goes out of that house means that air is going to go into that house, because we have a constant volume of air inside of our houses, measured in cubic feet per cubic feet. An average house has somewhere between 25,000 and 40,000 cubic feet of air inside that house. Obviously, bigger houses have more, smaller houses have less. But the air can move in and out of those houses just because pressure differences are created on that house, and there are holes in that house. We haven't been successful at building a completely airtight house yet. And there are three main forces or pressures that are fairly constant on our houses: the stack effect, the wind effect, and the mechanical effects, or mechanical pressures, wind pressures, and stack pressures that are in our houses. So let's describe stack effect, or the stack pressure. Stack pressure, it describes what happens to air as it warms. As air warms, it rises. And as air rises, it pushes against the upper planes of our houses. So this boundary between our conditioned space and our unconditioned attic spaces, it's in essence pushing against that space. And really it's seeking a hole. It's looking for a hole, maybe at a can light or a plumbing penetration or the gap between the drywall and the top plate. And if it leaves on that high side, it has to be replaced by air coming back in. And generally that happens on the low side of our houses through holes like crawl space vents or holes that are rim joists and box sill areas around our houses. You can see the stack effect demonstrated on this commercial building. You see the pressure and the air blowing up that balloon, in essence, on the outside of this building and sucking in the balloon on the lower side of that house. So that's stack effect. And stack effect is more pronounced in taller buildings. So as we're building these taller townhouses in our communities now, we see more accentuated stack effect. So if you go up to the top floor and you put your head over the stairway, you might even be able to feel the stack effect of air rushing up to that top floor there. Another pressure that is fairly constant on houses is the wind. And the wind is blowing on our houses, and it blows on the windward side of our house and creates a positive pressure. And on the leeward side, we get a negative pressure, which translates to pressures inside the building envelope as well. So if wind is blowing on the windward side and I have a negative pressure on the leeward side of my house, I might actually be sucking warm, moist air from inside my house through my building assembly to the outside if I have a hole on that leeward side of my house. And that can be a pretty impactful pressure in our houses that happens fairly often because we generally have a 1 inch square hole, 1 inch square of net free area hole every 6 to 8 feet around our house at our outlets if we're not doing a good job of sealing up those outlets or using airtight outlets. Now, mechanical pressures in our houses are generally created by fans, either our HVAC fan system or fans in our bathrooms, laundries, kitchens, and whatnot that are trying to take air from inside our houses to outside our houses. So these pressures are maybe not as constant as wind and stack effect, but they are also a pretty impactful pressure when we have imbalances in our houses. We can have imbalanced room pressures, or we can have imbalanced whole house pressures inside of our homes here. An example of that is duct leakage. If we have an imbalance, which basically means I have more leakage on one side of my system than the other side, I can create positive or negative pressures. So if we look at the picture on the left here, where we have more air leakage on the return side of my system, it means that I'm returning less air from inside my building thermal envelope and some air from outside my building envelope. Therefore, I'm pushing more air into the building envelope on the supply side than I'm returning from the building envelope, and I get a positive pressure. So I'm going to be pushing air against my exterior building thermal envelope and potentially pushing air through holes in that building envelope into it, or potentially all the way out of it. Again, air being a great transport mechanism for heat, moisture, and pollutants, I might be depositing that load into my building envelope just because I have duct leakage on the return side of my system. On the right side, it's just opposite here. I've got more supply side leak than I have return side leak. So I'm returning more air than I'm delivering to the system, and I'm getting a negative pressure and pulling air from the outside of my house through the building envelope there. So to summarize, air is a fluid just like water is a fluid, and we need a path and a pressure to be present for air to move through a hole. So I need a hole and a driving force or a pressure imbalance. And these driving forces can be created by stack effect, by wind, or by mechanical fans inside of our homes. If either are missing, I will not be able to move air across my thermal boundary. So one of the things that we can control more than we can control the pressures is the hole. So that's one of the reasons why we're trying to build that airtight structure to create a tight house where we have greater control and predictability of the air in that equals the air out here. Again, air is measured in cubic feet per minute, which is about the size of a basketball. So if a basketball enters my house, a basketball has to leave my house, or vice versa here. So why is this house a 100-year-old house? It's drafty, it's uncomfortable, but it's incredibly, incredibly durable. Well, it has tremendous drying potentials, but our expectations of our houses are changing the way that we're looking at our houses. So a lot of these older houses are getting remodeled and becoming more airtight. We're insulating them, whatnot. We're trying to gain predictability of airflow, heat flow, and moisture flow in our houses. But if we don't do that correctly, we might be driving air into our building assemblies and creating unsustainable housing. This house that lasted 100 years might fail pretty quickly after I do an energy upgrade on that house. And so we need to think about this airflow issue and the loads that air is transporting, not only from a new construction perspective, but also from an existing home perspective there. Okay, so let's move our discussion a little bit more directly to HVAC design, starting with our Manual J. So Manual J, again, is describing our entire building thermal envelope that is separating conditioned spaces from unconditioned spaces and governing how much energy is entering our houses or gained in our houses in the summertime, and how much energy is being lost from our house in the wintertime. So how much energy is leaving or how much energy is entering our homes depending on the season. Now, the first editions of Manual J were pretty basic. We basically used a lot of assumptions to assume what the load of that house was going to be. So this instruction said, you know, if the house fit into this cutout, then I put a 2.5 ton unit into that house. And so we've gotten better and better at utilizing a true Manual J calculation. And a true Manual J load calculation doesn't necessarily tell you what size your HVAC system needs to be. It tells you the actual load for that house. So we need to understand the difference between load and capacity. Ultimately, load is how much heating and cooling energy you need for that particular house that you're working on. And the capacity is how much heating and cooling the equipment needs to provide. So the capacity is in relationship to the equipment. You need to size the equipment so that it has the capacity to meet the load of that house, which means that the capacity of the equipment might be bigger than the actual load there, so that you have enough capacity to meet that load, but it can't be outrageously oversized to meet that load, because we're going to have runtime and just performance issues if we oversize the equipment too much or undersize the equipment too much. So we must have the capacity ultimately to meet the load, and the object of the Manual J portion of this equation is to describe what the load need is of that house. So when we're describing the loads, we have to describe the building thermal envelope that is trying to protect or resist the flow of those loads from leaving our house or entering our house. And we get into this problem of potentially oversizing our systems. And one of the reasons we end up oversizing our systems is if we right-sized our equipment for that house, but we used assumptions and those assumptions weren't carried out properly in the execution of the construction of that house, we're going to have a mismatch there. So for example, if I sized the house assuming that an R19 bat was going to be installed, and an R19 bat was installed, but it was installed so poorly that it's performing like an R7, then my system is going to be oversized and it's not going to perform. It's not going to actually create comfort in my house. It's going to create a system that's an energy hog, and our customers ultimately are going to be not happy with what's happening there. So a fundamental inspection question is starting to creep into our work when we're going out and evaluating houses at different stages of construction. we're no longer just looking at this question of, is it there? I can't walk into a house and just say, oh yeah, there's pink, yellow, or white in the wall cavities and leave and say, yes, it's there. I have to next look at how it's been installed and say, as it's been installed, does it actually work and function and perform? Obviously, on the picture on the right, we're using our cavity as a trash can rather than an insulated space. Here, we have to make sure that that gets repaired before the drywall is installed so that our thermal envelope will match our HVAC design and both systems will work and work properly. We need to see the synergy of things that are happening inside our houses. One way we can do that is to look at the manual J calculation and see some eight key components of that calculation and if they've been manipulated or not. Because some HVAC contractors are so worried about callbacks and having to go back to the house that they end up manipulating the HVAC design instead of trying to right size that HVAC design. So we need to look at the indoor design temperatures, the outdoor design temperatures, the square footage of the building components that are used in that assemblies, what actual R values and U values are they assuming are going to be installed in that house, the number of occupants and appliances in that house, the infiltration and ventilation loads in that house, the orientation, and then ultimately the duct location of that house. So let's look at these 8 requirements and then we'll conclude here. To begin with, let's look at the indoor design temperature. So the interior design temperature used for heating and cooling seasons are defined in our HVAC design because ultimately we're trying to create a delta T location across the building thermal envelope here. So the interior design temperature is assumed to be 72 for cooling season and the maximum of 75 for the, 72 for our heating season and a minimum of 75 for cooling season. So you can see that in the HVAC design for our winter design conditions. In this case, they use 70, and in the summer design conditions, they use 75. So you want to double check your HVAC design, the manual J, to see what the inside design temperatures are. Now, these design temperatures are based off of ASHRAE comfort zone chart. They've determined that during the cooling season, the design condition of 75 degrees and 55% relative humidity, 50% relative humidity is where the majority of people are comfortable during that season. And then the heating season at 70 degrees and 30 degrees relative humidity is the majority of time where people are comfortable during the heating seasons. Now these conditions again represent averages where people feel the most comfortable there. And that's why they're used as the design temperatures for the ACA Manual J here. Now the outdoor design temperature is also governed by ASHRAE, and it's historical weather data that's used to get that outside design condition. So for ASHRAE says that 1% of the time during the cooling season, the cooling dry bulb temperature is the temperature exceeded only 1% of the time, or 1% of the hours of the year. So during cooling season, it means that your temperature on the outside, if they're using 91 degrees for the cooling outside design temperature, it means that only 1% of the time is it getting hotter than 91 degrees. So it doesn't make sense to design to a condition that happens only 1% of the time. We want to design for a situation that happens, 99% of the time here. So we're not, although it does get hotter than 91 degrees, it doesn't get hotter than 99 degrees or 91 degrees enough during the course of a year to make that our outside design temperature there. Conversely, on the heating season, it says that during the heating, dry bulb temperature means that the temperature is above this point 99% of the time. So the outside design temperature in Denver is 1 degree. It means that 99% of the time it is warmer than 1 degree. So it doesn't make sense to design to -5 or -10 outside if we're not going to see that temperature very often. And if we build a sound building thermal envelope, if it does get colder or it does get hotter, our building envelope is able to swing with that hotter temperature because it's only, let's say in cooling season, it's only 100 degrees for a few hours during that day. And so our building thermal envelope should be able to swing through that hotter temperature outside, and our HVAC system will end up running for longer periods of time, which is ultimately more efficient here. So when we're creating these outdoor design temperatures and these indoor design temperatures, we're ultimately trying to create a delta T boundary for our thermal envelope so that we can measure the heat flow for heating season and cooling season that's moving through that building thermal envelope at these specific design conditions, which are deemed to be the maximum or worst case scenario design conditions that we're using. So it's important to ensure that the proper design temperatures are used so that we're not getting oversized or undersized equipment out there. Okay, so this was a study that the Department of Energy did that looked at if these outdoor and indoor design temperatures were manipulated, what was the consequence of that for the Manual J. And you can see that the loads changed pretty dramatically here. The loads increased by 26% during heating season. The cooling load, the latent load really increased incredibly, 113%. And the sensible load increased by 39%. A total load change of about 51% here for the HVAC design just by manipulating the indoor and outdoor design temperatures here. And this was for a house that was in Chicago here, which is the same climate zone as Colorado. So square footage of our houses can manipulate that heating load and cooling load as well. And this is where you would look for the area and volume of the house. So you want to check that it makes sense what they have. You know, a standard ranch house over a basement is somewhere between 3,000 and 4,000 square feet. So if you got a ranch style house and it was 8,000 square feet, you might want to double check the plans there and make sure that they did their takeoff right and they didn't make a mistake because that can really impact the loads of our house as well. The square footage of our houses are detailed out for each component. So in essence, we're looking at the wall components, the door components, the ceiling components, the window components, and we want to make sure that they did their takeoff again correctly here and they have the right square footage in each of those locations. If they put in more windows than are actually in the house during cooling season, it might lead to a larger air conditioner than actually is needed for that house there. Now, R values and U values are also shown on this component section of the Manual J. In this case, they're using an R19 drape insulation on their foundation wall and an R23 blown insulation in their 2x6 exterior wall here. So you can look at the U values and the R value that is listed here. And one thing that's interesting here is if you look at the R19 value that's on the foundation wall and you look at the U value, you'll see that they don't equate to each other. So an R19 U value should be 0.053. They put 0.032, which means that it's actually insulated better than an R19 here. The U values are used in the calculation of in the software calculation there. And Therefore, you want to make sure that they're using the right U values. So again, that they're not going to ultimately be oversizing or undersizing the equipment here. It turns out that they have the right U value for the R23 above grade wall here. Now, this study looked at wall components or thermal envelope components as well. You can see that they used worse window than their baseline or their specifications called out for. They used worse wall insulation and worse attic insulation, which equated to a change in the load. Again, it increased the load on the house and would cause a larger furnace or air conditioner to be installed in that house. A total change of 24% by this manipulation here. The number of occupants. So occupants can inflate the load as well. An occupant equals the number of bedrooms plus one in our house. So you can calculate if you're doing a review, if you know how many bedrooms are in that house, you can see how many occupants should be added. The manual J assigns 230 BTUs per hour per person that is equated to that particular house and that particular design. So in a 5-bedroom house, you should get about 1,300 BTUs per hour there. Now we've seen a manual J where somebody input 23 people into the house. That equated to obviously 17 too many people, which was an additional load of almost 4,000 BTUs per hour that were added to that design there. So this was another way that designers are either making mistakes or adding people purposefully to oversize the equipment because in their mind anyway, they think that they won't have to come back to do a warranty work on that house. But often you're seeing that these oversized equipment are performing so poorly that the HVAC contractor has to go back anyway to deal with short cycling systems or other types of systems. This ultimately resulted in a 1/4 ton of additional capacity that was added to this house that actually wasn't needed in that house. Occupants in this 3-bedroom house, you can look at the internal gains here and see in the worksheets for RightSoft. This is a RightSoft software, and you can see what the internal gains have been added for occupants, in this case 4 occupants, and it was done correctly here. Appliances in the same way are shown here. You see the appliances here and about 2,600. So appliances are generally added for refrigerators and dishwashers. Those appliances that run often. So generally speaking, only 2 appliances should be added to an HVAC design. And roughly speaking, about 1,200 to 1,400 BTUs are assigned per appliance. So in this case, it looks like at 2,600 BTUs that they have taken into account 2 appliances in that equation. So again, if you did a review and you saw 4,600 BTUs here, you might question what they're taking into account from an appliance load perspective here. Infiltration and ventilation. So infiltration and ventilation are looked at separately in our HVAC design process. And on the manual J, infiltration is either a choice or you can use an estimate there. So your choice is to use an accurate measurement or an estimate of the infiltration in our houses. The infiltration estimate introduces all kinds of uncertainty, subjectivity, and accuracy questions into the equation. So obviously it's better to use a more accurate number, but that accurate number comes from a blower door test, and you need to ensure that you've done enough blower door tests for that particular builder to have some consistency or consistent average that you're going to use there. The manual J infiltration, again, estimates are conditional depending on the size of the dwelling unit and potential sealing efforts that are done there. So The manual J makes some assumptions about the number of can lights and the number of fireplaces and ultimately how airtight windows are and backdrafting dampers. All these different things are kind of subjective estimates that manual J uses to determine the air tightness level. Their method for infiltration is using these estimates. You can choose from tight, semi-tight, average, semi-loose, or loose. And these are kind of the descriptions that are given to each of these. Again, it's not a very accurate way of choosing the infiltration rate of our houses here. The infiltration rate is listed on the design information. In this case, they use semi-tight as the method for infiltration, and the construction quality was used as tight here. And we'll see in a second here where that translates into a load as well here. So you see that the average air changes per hour is in a 0.13 number here. We need to talk about that as well, which we'll talk about in a second. So keep that in mind. The infiltration rate here is on the worksheets as well. And you can see in this case that the infiltration rate added 3,392 BTUs to the load in heating season and 423 BTUs to the cooling season load here. There is a newer version of manual J out that's looking at heating load, sensible load, and latent loads and divides that out slightly differently here. So you might see this as well, so I wanted to show you that as well. Now, going back to how air leakage is measured in the manual J, it turns out that air leakage is measured in natural air changes in the manual J, whereas the IECC and a lot of other folks measure in air changes per hour. So we need to understand a little bit the difference between the two. Air changes per hour is the number of times the volume of air in a home exchanges with air from the outside, whereas natural air changes is the number of times the volume of air in a home exchanges with that air from the outside, but it's adjusted for how tall the building is, what climate that building is, and how exposed that building is to the wind out there as well. They're calculated slightly differently there with this N factor that takes into account the climate, the height of the building, and the exposure of the building there as well. So just to give you an example of the difference here, if I have this two-story house that's 2,500 square feet, the air leakage of this house is 2.67 air changes per hour at 50 pascals, whereas its natural air change is 0.18 natural air changes there. So when you are using an estimate for the manual J, it will be detailed out as a natural air changes, but you can input the actual air change number if you know the average that that builder is using. And it is better to use the actual air change number than these estimated numbers so that you're getting a more accurate depiction of that there. So the ventilation now is also looked at in the manual J, and it's looked at separately there because the code is saying that we have to ventilate our houses, and we can use either exhaust, supply side, or a combination, which means balanced ventilation inside of our houses. So again, we can use positive or supply side ventilation, negative or exhaust side ventilation, or a balanced ventilation system, which would be currently through ERVs or HRVs in most cases there. Now, ventilation can add a substantial amount to our heating loads here and to our cooling loads there as well. And so we want to look at what type of ventilation is being used. This is a central vent ventilation system. It's taking outside air to the inside. So this is considered a supply side ventilation system here. And you see that it's adding a load to both the heating side and the the sensible side. And this load is in addition to the infiltration load that we talked about before. So that's why we really need to understand these things separately here. The ventilation in exhaust ventilation systems is a little bit different here. So we see the infiltration and the room ventilation. And for exhaust ventilation systems, they tend to get put together because the assumption from Manual J is that exhaust ventilation is coming through random holes in the building envelope, which is potentially true, but and infiltration is also coming through random holes in the building envelope, but exhaust ventilation is put under a specific time period and a specific rate. So if I have an exhaust fan that is exhausting air out of the house, it's exhausting it at a specific CFM rate and a specific time period, which is different from infiltration. So you really should count infiltration and ventilation loads separately, and it just gets harder when you use exhaust ventilation. So make sure that you're figuring out how to do that properly when you're using an exhaust ventilation strategy there. These loads, again, impact our HVAC designs pretty dramatically here. We see that here the infiltration loads were manipulated, and we got an increase in our loads, in our heating loads by 12%, in our latent loads by 28%, and our sensible loads by 3%, and a total change of 7% here. So quickly, let's look at orientation as well. In this case, you can get the loads for the northeast orientation, the south orientation, and all the major cardinal directions. You can see how the load has changed. There's a difference of 6,200 BTUs, which is about a half a ton of AC there. Energy Star would require that you do a second design because it's more than 6,000 BTUs different here. And so you need to, Energy Star is a best case scenario here. If you're not doing cardinal specific or site specific designs, it makes sense to do, to look at this design chart per orientation and make sure that you're doing different designs if you have more than 6,000 BTU difference per cardinal direction there. Duct location also makes a large difference because if you have ducts located in your attic, the insulation that we tend to put on that duct is not really enough to impact the amount of heat loss that's happening through that duct or heat gain that's happening through that duct there. You can see if you have ducts outside your building envelope on your duct design. In this case, we have the large returns that are up in the attic there. So you can look for the duct location there, and you can see that duct location on your HVAC design. And it impacts our ducts, our design pretty dramatically here. We get a total cooling manipulation of about 17% in this case because of duct location and duct conditions here. So if we look at all the manipulation if we added all the manipulations of these 8 points together, we see a total cooling manipulation of about 97% and a total heating load manipulation of about 55%. It's pretty dramatic. The city of Fort Collins did a study a few years ago, and they were seeing that HVAC systems were oversized by as much as 100 to 300% there. So it is happening out there in the field. If you do a proper HVAC design with the right design conditions and the right assumptions, the system itself is oversizing our system. So these manipulations compound that and exponentially change that load there. So we don't want to see these types of manipulations. And the big point here is that ventilation and infiltration should be counted separately as loads. And then we need to carry out that building thermal envelope correctly. There are some other sources of air that aren't taken into account very well. Combustion air potentially needs to be conditioned, and makeup air for kitchen hoods also potentially needs to be conditioned. What the code is doing for combustion air anyway is it's saying that rooms containing fuel burning appliances that utilize combustion air, you need to create an airtight room around that combustion air appliances, in essence putting that combustion appliance outside the building envelope there. And so some jurisdictions are enforcing that and others aren't, but that is something that you need to consider. So it's also a general nudge to consider sealed combustion appliances to ensure that we're getting appliances that can't backdraft, create combustion safety concerns, but also appliances that aren't adding kind of random loads to our houses. Okay, so to conclude here, we need to really take into account the synergy between the envelope and the HVAC design. If we are designing our systems early in the process and we're making assumptions about the building thermal envelope, we need to link the execution of that building thermal envelope to the ultimate performance of the HVAC design, the HVAC system and its performance. So it's crucial to do the inspection process with this new kind of mantra in our heads. Is it there and does it work? Is the insulation there? Are the air barrier systems there? Have they been carried out in such a way that they actually perform and work? We need to remember the different air streams that are out there, from air leakage, infiltration, and exfiltration, ventilation systems that are in our houses, combustion air and makeup air, and that each of these things have a load, that air in equals air out, and all of the air that's moving through our building envelope has a load that needs to be accounted for separately. Ultimately, we're trying to gain predictability, control of that airflow, moisture flow and thermal flow in our houses. So we want to build tight and we want to ventilate correctly, again, to continue to gain control and predictability throughout our houses. I want to thank again Xcel Energy, the City of Fort Collins, and the Northern Colorado HBA for helping us put on this educational series. I look forward to seeing you next week. And if you have any questions, I'm more than happy to stay on and talk with you a little bit longer here, or you can reach out directly to me at my contact information that's on this slide here. Thanks again for taking part, and we will answer some questions now. Okay, so the first question we have is, what manual J infiltration rates should be used in our area in cities on current codes? In most cases, we should be using tight. If we're looking at the 3 air change requirement there, because we're most often building tighter than 3 air changes. In jurisdictions like Colorado Springs, for example, that have amended their code to 5 air changes, you might get away with semi-tight, but the reality is that most builders are building way tighter than 5 air changes per hour. So tight would be a good assumption, but again, it would be better yet to get some historical data from builders on the tightness of their homes through blower door testing, and then ultimately transition to using more accurate information from those blower door tests in the calculation. It says, how do I see recorded versions of this webinar? The recorded versions of this all of these webinars are being hosted on the Northern Colorado HBA website there, so you can get that. The next question is, should we all have contractors submit manual J's and S's when they replace existing equipment? And D, when they replace ducts? It is always recommended to redo a manual J, S, and D, well, at least at a minimum a manual J when you're working with existing homes and existing equipment. What happens most often is that contractors replace existing equipment with the same size equipment for the new that's going in. So if they're replacing 100,000 BTU furnace, they're putting in 100,000 BTU furnace. But that house might not need a 100,000 BTU furnace. That house might be seeing short cycling of their HVAC system or freezing of their coils or other things like that that are indications that the system is not sized properly. So a manual J will help determine the correct load for the house, and then the manual S will determine the proper sized equipment that has the capacity to meet that load. And it makes sense to do that on an existing home as well as a new home. You might have to make some assumptions or do a good detailed energy audit on the house to understand how that house is insulated, how airtight that house is on the existing home side in order to be able to do a proper manual J. But all that work ultimately is worthwhile to do. And the City of Fort Collins has a great energy auditing program for existing homes, so you could probably get that information pretty easily. Do we also have the existing rooms sealed when there is combustion air in the rooms in the envelope? I assume that question is for existing homes. My guess is that most jurisdictions would not enforce that on an existing home, but they should be enforcing it on a new home. On an existing home, it would, however, be worthwhile to do a combustion safety test on that home to ensure that especially the atmospherically vented water heater is not backdrafting because of leaky duct work or because of excess exhaust ventilation that might be in that house. Okay, it looks like that's the end of our questions. So again, I really appreciate your time today. If you'd like to reach out to me, don't hesitate to reach out. I'm more than happy to communicate with you. So have a great day, and we'll see you next week.